Okay, so we talk about field now. So let us just recap what we have. So we have defined the ring. So what, just to recap, what is a ring? So we have a set R with two operator plus and dot. Then ring is basically we have the algebraic structure which satisfy this property with this operator, like we have R with plus is an abelian group. Abelian group. So abelian group means it is closure, associativity property, existence of identity, then existence of inverse for each element, and also commutative. This plus is commutative, that is why it is abelian group. Okay, and then with dot we need to have a semi group only. Semi group means we have only closure and associativity property. Okay, so then it is a semi group. So and we have distributed law. So A dot B plus C is equal to A dot B plus A dot C. Both the way we should have left distributed law, right distributed law. So A plus B dot C is equal to A dot C plus B dot C. So if this satisfy, then it is called a, this is a ring. Okay. Now we say this ring is a commutative ring, because this plus is already commutative, it is abelian. So when we say it is a commutative ring or abelian ring, if it is also commutative under this dot, if so along with this, if dot is commutative is abelian. So that means if A dot B is equal to B dot A for all A B. If A dot B is equal to B dot A for all A B, then it is called commutative ring. If it is commutative, then these two property are, these two distributed law are same, because it is commutative. So we can take this way, that way, it does not matter. So we have only one distributed law, okay, because this is commutative operation. This is called commutative ring. Now we will just recap ring with identity element. So along with this, if we have identity element or unity element for, so ring with unity or identity element. So when we say if this is a ring such that this has a identity element. So we have identity element under this dot. So that means there exists an element which we denote by 1, because this is a multiplicative sense we are taking, or if you okay, we can say E1 identity element correspond, but anyway 1 is okay, just a sense of such that this is in the set R such that A dot 1 is equal to 1 dot A is equal to A for all A. Then we call this is a ring with unity. Okay. These are all defined in the last class. Now we talk about divisor of 0. Okay. Divisor of 0. 0 is the additive identity of the ring, additive identity of the set, okay, of the group, because that 0 is the so we have a R plus, so 0 is the additive identity of this. So A plus 0 is equal to 0, it is commutative. So this is same as 0 plus A is equal to A. So this 0 is the additive identity of this group. Okay. So, when we say so suppose you have a ring R and suppose this is a non-empty set is a ring, this is the definition of the divisor of 0. Then a non-zero element say A from this set is said to be a divisor of 0 if there exists a non-zero element B such that A dot B is equal to 0. This is the right divisor. A dot B is equal to 0 or B dot A is equal to 0. This will be the left divisor. Okay. So, but if dot is commutative, then both are same, both divisor are same. So, A will be called a divisor of 0. A has to be non-zero if there exists a B which is also non-zero such that A dot B is equal to 0. If such A exists, I mean then A is called a divisor of 0. Okay. So, now this is a left divisor and this is right divisor. Now, if this is a commutative ring, then both the divisors are same. Now, we will take an example of divisor. Suppose we are talking about Z6. We know Z6 is the modulo class of 0 to 5. So, that means this partition the all integer into this 6 classes. So, if you take any integer, if you divide it by 6, then the remainder will be either one of this. So, it will just the partition the set of integer into 6 classes. Okay. And we know that Z6 along with these two operators is a ring. Okay. Now, we can say 2 is a divisor of 0. Divisor of 0, because for 2 we can just 2 multiply with 3, it is basically 6 mod 6. This is the operation, this is the star operation. So, it is basically 0. Okay. So, 2 is a divisor of 0, even 3 is a divisor of 0, 4 is a divisor of 0, because 4 into 3 is 12, 12 is basically 0 under this dot operation. So, dot operation is nothing but A into B mod 6. This is the how we define this dot. Plus is also same, we will take the plus and then mod 6. Okay. So, this is an example of divisor of 0. Now, if we take Z5, then it has no divisor of 0. Z5 has no divisor of contain no divisor. No divisor of 0. Okay. Similarly, set of all integer, this also contain no divisor of 0. Q no divisor of 0 or no divisor of 0. So, these are the example where these are having no divisor of 0. Okay. So, now we define integral domain. This is another algebraic structure. Integral domain. So, this is also need to have a set R along with the two operator. So, is called, this algebraic structure is called an integral domain if the following satisfied. What are those? First of all, it has to be a it must be a ring, not only ring, it must be a commutative ring with identity and no divisor of 0. So, first of all, commutative ring with unity and no divisor of 0. Okay. So, what do you mean by commutative ring? So, that means this must be a ring along with the star must be commutative, is a ring and the star must be commutative, that means A star B is equal to B star A. And unity means we already have the identity element for the plus, because this is a ring. So, now we talk about the identity element for the dot, then it is called unity. So, if we have an element such that A dot 1 is equal to A for all A, then it is called unity element. This is called identity element under the operator this multiplicative sense. And no divisor of 0 means if A dot B is happen to be 0, 0 is the identity element under plus. If this, then either A is equal to 0 or B is equal to 0. This is the meaning of no divisor of 0. So, if AB is becoming 0, then either A or B has to be 0. Okay. So, that is the meaning of this no divisor of 0. So, if this satisfy, then the algebraic structure R along with these two operator is called a integral domain. Okay. So, now we can take some example of the integral domain. So, some example. So, like Z set of all integer, this is an integral domain, because we know this is a ring Okay. Ring means we know this is an abelian group and we know this is a semi group and also we know the distributed property. This is the ring and also the right distributed, this is the right and left and right distributed property. So, this is the ring. Now, we can have a yeah. So, now this is commutative, this is a commutative ring star, because this is the multiplication, real number multiplication, and this is over z. So, we know the real number multiplication is commutative. So, this is commutative, and also we know there is a one identity element such that if we take any integer okay. So, this is the ring, commutative ring with unity. Now, it has no divisor of 0, because if we take any two integer say a dot b, if it is 0 means either a is 0 or b is 0. There is no so then this implies a is 0 or b is 0. Otherwise, no two non-zero integer can give us a 0. Okay. So, this is an example of a integral domain. Now, another example is R plus, this is also an integral domain, set of all real numbers, and if you take Z5, Z5 is also an integral domain. Z5 is the set of all, if you take the mod 5 operation, this is will give us the residue classes of all mod 5. Remainder is 0 to 4 basically. But if you take Z6, this is the plus under the mod operation. This is not an integral domain, although this is a commutative ring. Commutative ring with unity, but not an integral domain, because it has a 0 divisor. 3 is a 0 divisor, 4 is a 0 divisor, 2 is a 0 divisor, not an integral domain. This is an example which is a commutative ring with identity, but not an integral domain. Okay. So, now we define the field, which is another algebraic structure. We defined field. Okay. So, suppose this is a set F, non-empty set, along with the two operator. Since it is field, we denote the notation as F, set notation. For ring we use R notation, but for field we use this F notation. Okay. So, this is a field if certain properties are satisfying. What is those? First of all, it has to be a okay. It is an integral domain. Integral domain. Okay. So, integral domain means what are the properties we have? It is a commutative ring with unity and no divisor of 0. And along with that, if it has a inverse, multiplicative inverse, if for each non-zero element has a multiplicative inverse, for every non-zero means the 0 is the additive identity of the plus of this field, of this set. Every non-zero element has a inverse, multiplicative inverse. Then it is called a field. So, every non-zero element has a multiplicative inverse. So, if it is having multiplicative inverse, then it is basically a group. Okay. So, now we will formally just jot down all the properties of this to be a field. So, we have this set F. So, let us just jot down the property when it is a field. So, first of all it has to be a ring. So, okay, let me just write all the operations. So, A plus B must belongs to F, for all A B belongs to F. This is the closure property of this plus. Okay. Now, associativity property A plus B plus C is equal to A plus B plus C, and this is for all A B C belongs to F. This is the associativity property. Now, existence for identity, multiplicative identity, which we usually denote by 0. A plus 0 is equal to 0 plus A is equal to A. So, this is F. Okay, and now we have the inverse for every A belongs to F, there exists a element belongs to F such that A plus is equal to 0. Okay, so, this is the inverse. So, every element has a additive inverse. Now, along with this we need a, so this will give us a, up to this will give us F is a group. We know the definition of the group, F is a group, but we need this to be a abelian group. So, we want A plus B is equal to B plus A. So, up to this meaning that this is an abelian group. Okay. Now, this is with the plus operation. Now, we have with the dot operation also we need to have a few properties like A dot B must be belongs to F. So, this is also closure property of dot. Now, we must have the associativity property A dot B dot C is equal to A dot B dot C for all A B C belongs to F. Now, we have, so we have inverse. So, identity element of the dot. So, there must exist a one such that, so this is a unique element such that A dot 1 is equal to 1 dot A is equal to A, and this is true for all A. Okay. And then this is the identity element, multiplicative identity, so which is called unity also. And then we have this inverse for non-zero element. For every A which is not equal to 0, there exists A inverse such that A dot A inverse equal to 1, such that A dot A inverse equal to 1. Okay. So, this is the inverse, and we need to have this to be a commutative. So, A dot B is equal to B dot A, and this is true for all A B belongs to A. So, this will give us F is an abelian group. And we have the distributed property. So, A dot B plus C is equal to A dot B plus A dot C. This is true for all A B C. Here it is commutative. So, right distributed and left distributed are basically same. Okay. and yes. So, right distributed and left distributed basically same. So, these are the all properties we should have in order to get the field. Okay. So, up to this, so say up to this, up to these two are semi up to this, along with this distributed law with the right distributed also, it is a ring. Now, if we include this one, this is a ring with unity. Now, if we add this, this will be ring with commutative ring with unity. Now, if we add the divisor no divisor property, then the ring, this is the integral domain, and then if we have the existence of inverse, if we add, then this will give us a field. So, this is the hierarchy. Now, we quickly take some example of field. Okay, so, Z real number, sorry, Z is not a field, this is not a field. Why? Set of integer is not a field, because inverse is not there. Okay, because if we take an integer n, then multiplicative inverse is 1 by n, 1 by is not an integer. So, this is not a field, but if you take the real number, set of all real number is a field. Okay. Because any non-zero element, if we take a, if a is not equal to 0, then 1 by a is also belongs to R, that is the inverse. So, this is a field. Even complex number, set of complex number is a field. These are the complex number addition and multiplication. Set of all complex number is a field. Now, Z5. We know Zn, Z5, this is a field. We can show this is a field, we can show this is a abelian group, we know this is an abelian group, and if we exclude 0 from here, this is also an abelian group, and we can have the distributed property, say A dot B plus C is equal to so this is the field. Since the number of elements here are finite, there are only 5 elements over here. So, this is also called finite field, because number of element is finite in this set. So, this is also called finite field. Okay. So, field is a algebraic structure which is having two operator with this properties. Thank you.